Hi, Pedro. Thank you so much for joining us today on Conversations at the Perimeter.
Thank you. Thank you for having me. It's fun to be here.
So I want to start by admitting I was a little bit nervous to interview you today at first, because a lot of your work relies on quantum field theory. And as a teacher of some subjects like that, I'm maybe used to a different pedagogical approach where one might first take an undergraduate degree in physics, study some classical mechanics, special relativity, take a graduate course in quantum mechanics before even mentioning the term quantum field theory. But of course, we're not going to walk through all of those prerequisites today. So I thought, how are we going to talk about Pedro's work with all of those things that usually come before? But we had a conversation with you, and you were so great at explaining what you do. So now I'm not nervous. I'm just excited to hear how you're going to explain all of these complicated concepts. And so maybe we can just start by asking you, what is a quantum field and what is quantum field theory?
In physics, the two main theories that describe physics, as you said, are quantum mechanics and relativity. So those, if you want, are the very basic principles of all of physics. So relativity tells us about space and time and how things behave in space and time. It even tells us what is space and time. I mean, how space can become time and how time can become space, and how do we measure distances, how do we measure times, and what are points in space and time, where do things happen and when do things happen, and so on. And quantum mechanics is the theory that describes particles, that describes the most fundamental objects of the universe, our microscopic particles that move in this space-time. And what we understood is that one way of understanding what are particles that move in this space-time is by imagining that there is this fluid-like quantity, this field, that permeates all of space-time. So a field is just a way of assigning to each point of space and time some quantity. That quantity could be the temperature in a room. To each point in the room, there is a temperature. It can be the velocity of water inside a swimming pool. To each point inside a swimming pool, there is a velocity of water there. It can be the magnetic field in the universe. To each point around us, there is a magnetic field, stronger close to the sun and weaker farther away. And in particular, particles themselves are excitations of fields. You can imagine that all our fundamental particles are understood as small waves of fields that permeate the universe. And so field theory is the language that puts together quantum mechanics and relativity. It's all about space-time, it's all about this arena where things move. And it describes not only the arena where things move, but the things that move themselves as excitations of some kind of a field-like object. We can picture it as like a membrane that can be still, and then there are some small ripples of this membrane, of this sheet that move around, and these small ripples are particles that make us and the universe.
And what is quantum about this description?
So quantum mechanics is the theory of the world of particles, and the very basic feature of nature and of quantum mechanics is the idea that many things can happen at once. And so that when a particle moves from a point to another, what's actually happening is that the particle is going through all possible trajectories at once. And that's very surprising, because that's not what we see in our day-to-day, right? We throw a ball and the ball goes along some trajectory, and I throw the ball, you catch the ball, you throw the ball back to me. We don't see the ball going in all directions. And the reason is just that the most important trajectories dominate the physics, they dominate the process, they are more important, and when you compute indeed you realize that there are some trajectories, some classical things that are happening that are much more important than others. But strictly speaking, and in particular when you go to the microscopic world, all these things that can happen are happening at the same time and they matter. And so when you have these fields that describe these particles, these fields are not quiet. They are not just some boring membrane that is still and then there is a particle here that's moving and following a straight line. Instead, these fields are vibrating, and these vibrations are what we call quantum mechanical vibrations. Many things are happening at once, and in fact, everything is happening at the same time. And these particles are all interacting with each other, moving in all possible trajectories, and swapping, throwing particles at each other. That's how particles interact, right? Particles deflect because they throw stuff at each other. And so they are coming into collision, but they throw stuff at each other, and they deviate, and they deflect, and they interact with each other, and that's how nature works. And this might start to look very complicated. How are we going to describe things that happen? If I tell you that to describe what happens, you have to describe everything that can happen.
That sounds impossibly complicated.
It sounds complicated. And the way out is because, as I said, there are things that matter more than others, right? So when you throw a particle in the middle of empty space, the thing that matters most is when the particle goes in a straight line from point A to point B. Then there are other things that can happen. The particle can emit some other particle that can be absorbed later and so on. But that, it's a little bit less likely. And it can emit 2 or 3 particles, and that's even less likely. And there is a notion in physics of decoupling. And decoupling is it's a parameter that it's what quantifies how much of these quantum fluctuations are going on. Are you studying a system where if you want, decoupling is small, where these quantum effects are small and where things are not as bubbly as they could be? Or are you studying something where the coupling is big and really everything is happening at the same time? Mm-hmm. And most things we study, the coupling is small and not much is happening. And yet, that describes most of what we see. Take, for example, light. Light, for the most part, just goes straight. Right? We turn on a flashlight, and what's happening is that a gazillion photons are going from the flashlight to the wall.
Is that the actual number?
Probably.
Give or take?
Maybe 3 or 4.
Okay.
Gazillions.
Got it.
So 3 or 4 gazillions go from the flashlight to the wall. And what do as they travel? They go all together, right? Quiet, like very respectful photons, all by each other. And they just go, and they go from the flashlight to the wall. They are not struggling. They are not fighting with each other as they go. They are not like a bunch of hooligans. They are really going calmly from the flashlight to the wall. And so that's an example where not much is going on. Mm-hmm. So it's true that to describe the photons, we don't describe just a straight line from the flashlight to the wall. We describe the other trajectories, but they really matter very little. And so that's an example of a system that is weakly coupled. So the photons, they also interact. They interact with the air. They heat the electrons in the air. Mm-hmm. That's why we see the light when the light, because it's from time to time hitting some particles in the air and being deflected into our eyes.
Right.
But for the most part, most of the light goes from the flashlight, and we see just a spot of light on the wall. And so when things don't interact much, this taking into account all the possibility in practice means taking account a few possibilities. Because the craziest ones don't matter, right? We don't consider the trajectory of a photon where the photon, instead of going, photon are particles of light. When the particles of light go from the flashlight to the wall, if instead of going directly, it first goes around the room and then it goes, that's going to be an irrelevant contribution to what's going on. Now, that's not always the case. So sometimes there are situations in physics where really this craziness of quantum mechanics, where everything is going on at the same time, matters a lot. And an example is what happens inside the nucleus. Inside the nucleus, we also have particles like photons. What do I mean by like photons? It's particles that don't have mass, that are very, very light. They are called gluons instead of photons. And the main difference between the gluons and the photons is that the gluons, when they move, if I had a flashlight of gluons, and if I would turn on my flashlight, instead of the gluons propagating from the flashlight to the wall, they would start fighting with each other. They would start having these brawls and fighting and making balls of energy of gluons, and they would end up being stuck in this big fight. And by this fight, I mean all these quantum effects going on.
I want that gluon flashlight. That sounds fascinating.
That's what keeps us. That's what makes us alive, because the gluons, the name gluons comes from glue. And what they do is this crazy fight of the gluons is what keeps the constituents of the nucleus together.
Right.
So you could imagine that you put many, many protons together at the center of our atoms, and the protons, they have all positive charge. Why would they want to be together? They don't, right? They hate each other. Particles with positive charge, they repel. So you put a bunch of protons together, the first thing they want to do is each one they wants to go apart. And yet, our nucleus is full of a bunch of protons, right? So what is happening? Who is keeping them? They want to fly apart, but all these gluons are there fighting with each other. And so the protons cannot get away because they are in the middle of this fight. They're just looking, oh my God, let me stay here. Because there is all this gluon fight around them. And it's this, and by this fight, I mean that the gluons are behaving in all possible ways. Everything is happening. They are moving left, they are moving right, they are moving up, down, all at the same time. And we really need to take all these quantum effects into account.
Another way to say this is that they're strongly coupled?
And that's another way. They are strongly coupled. So the probability of the gluon going straight is as likely as the gluon splitting into two gluons or turning right or turning left, and everything matters at the same time. And it's not true, like with the photons, that you just consider something simple, like going straight, and the rest doesn't matter. That's not true with gluons. And that means that when you say the world is described by quantum field theory, that's totally true. But quantum field theory gets split into two quantum field theories, if you want. You can call it the easy one and the hard one.
I'll go for the easy one, please.
Yeah, when the coupling is small, you get the easy one. Some things happen, but not much. You can control what's going on. And you can compute what's going on and improve slowly your computation. You can say the particles of light go straight, plus a small deviation, plus a small deviation, plus a small deviation, and step by step you improve your calculation. Right? So in school you learn, then you go to graduate school, you learn how to correct it a little bit more, and you keep improving. And this is fantastic. It works amazingly, and in many, many situations, it's what allows us to test physics with these crazy number precisions, where we have all these analogies that we measure distances in particle physics within the precision of an air and stuff like this. And but sometimes, when quantum effects are strong, sometimes we have a qualitative picture of what's going on. We kind of understand in cartoonish terms what's going on. We understand the protons, they need to be stuck there because all these gluons are fighting with each other. But this is a cartoonish picture, right? I'm speaking with my hands, literally, right? in saying this. Now, if you want to ask me, okay, given that you know that gluons interact in this crazy way and that they hold the protons together, can you from that, and even they allow the proton to exist because the proton itself is made out of these quarks, and quarks, they also would like to get away from each other, and it's the gluons that keep the constituents of the proton together. So given that gluons are so important in maintaining the stability of matter, can you, from the dynamics of the gluons, tell me what's the mass of the proton? Tell me about these fundamental properties? And the answer, for the most part, for these very tough questions that involve controlling strong coupling is no. Our mathematics is not good enough. I cannot sit with a piece of empty paper and start my computation, step one, the glue, and compute, and at the end, give you the mass of the proton at the end of the page, or at the end of 20 pages or 50 pages. That's not possible. We don't know how to do these computations. So, and that means we need to develop these new tools. So we need to understand quantum fields when they are easy, but that we kind of understand. It's just about computing more and more. So you suffer and you get 3 decimal places. Then you suffer more and you get 4 decimal places. Then you suffer even more and you get 5 decimal places. And the more you suffer, the more decimal places you get. And then you have the hard quantum field theory that is not even about suffering. It's that you don't know where to start because everything matters. I need to compute everything. How do I compute everything? I don't know how to compute everything. And you need new tools. And some of these tools are, for example, using computers, like what you, Lauren, do. And some other tools could be trying to develop what could be the new ways of thinking about quantum fields that allow me to develop some techniques for studying what could happen in these crazy situations where quantum mechanics is so strong. And by the way, typically that also means that relativity effects are very important because when things are happening a lot at these very high energies and things are vibrating a lot, they are moving very fast. And when things are moving very fast is when relativity is important, when space and time get entangled with each other.
So both quantum theory and relativity
both
are
quantum
at play.
theory and relativity are at play. Everything is happening at the same time. We need new rules. We need new ideas to think. And I would say that's one of the key things we try to do at PI is understand what are these new ideas that we need. How do I describe quantum nature when quantum effects are the dominant thing and when everything is happening at once? Do we just give up? Or what do we do? And
so what do you do? what would you see as the end goal, if you could say, what would be the eureka moment if you could suddenly calculate these things? Where would that take us?
So another way of saying it is, when do we care about these very strong effects? So I told you already one example, which is to understand the matter, to understand the stability even of matter and what holds us together and what makes a nucleus and fundamental particles stable. So understanding matter and particle physics is one of the ultimate goals. But maybe more conceptually, another very important situation where we would need to tame these very quantum effects is when we try to understand how to merge quantum mechanics and relativity into what is called the theory of quantum gravity. And so what happens is that we understand very well the rules of quantum mechanics when quantum mechanics is important. We understand very well the rules of relativity and of Einstein's theory of relativity, of gravity. When we try to put both together, we don't know how that works. We don't know what are the rules of the game. When I need to use at the same time quantum mechanics, that's very important, especially when things are very small. And then when things are very small, everything that can happen will happen, and you have to take all that into account. And gravity, that describes how the space-time can itself be deformed and because that is actually what gravity is. Now, normally we don't care, because normally when space-time is deformed is when you have some kind of huge star that is bending the space-time or a black hole or something. And typically, when objects are huge, quantum effects are irrelevant. And when quantum mechanics is important is when we are studying electrons or protons or photons, but then they are very light and they don't deform space-time. On the other hand, when you are close to singularities of black holes or at the beginning of the universe where everything was squeezed together in a Big Bang, then you cannot get away without using both at the same time because things are both very heavy but also very small. And that's a key thing. We want to understand what are the ultimate rules of the game? What describes really our universe and what's the ultimate theory of physics? And that ultimate theory needs to deal with strong coupling. So developing these mathematical tools is useful both for real-world physics, for understanding how do protons behave, how do some materials behave, because not all materials are weakly coupled. Sometimes we have in regular materials what are called phase transitions. And these phase transitions are precisely points in the material where everything is happening at the same time and at all possible scales, and everything is very important there. All these quantum effects are very important. And so taming these strongly coupled effects are important both in these real world situations, but also they will be needed to understand what's the ultimate theory of quantum gravity, what's the ultimate theory that describes our universe and that puts together all the rules of physics that we know into a unified rule.
Mm-hmm. And we can't go to a black hole or the beginning of the universe, so it has to happen largely on blackboards at first? Is that
right? So one of our key tools. So what do we use? How could we do progress in such field where things are so abstract and where you are trying to even develop the rules of the game?
Mm-hmm.
So what do you use? So you use lots of thought experiments. Like you said, you cannot jump into a black hole, but you can do a thought experiment. Suppose I throw Alice into a black hole, and Bob stays outside, and Bob sends a signal to Alice. And as Alice is falling into the black hole, she keeps sending the signal back to Bob at the rate of 3 photons per second, etc. And you do these thought experiments, and you start imagining what would happen if you do if you go to these extreme situations. And often these thought experiments allow you to deduce, to come up with new rules for how physics work. So that's how Einstein developed many of his ideas, was by imagining if I'm falling, he had these experiments where you would jump, and if I'm falling and something is falling nearby me, how can I tell that I'm falling? I look at this red ball that is just falling with me. How do I know that we are both falling and we are not both just standing in space?
Mm-hmm.
And indeed, you cannot. If all you see is the red ball that is close to you and you are both falling, you see the red ball and you are falling, or you are in the middle of empty space, it's the same thing. And so he said, basically then gravity should just be like falling, should just be like going freely in empty space.
Mm-hmm.
And then maybe gravity can be geometrized, and maybe gravity is just deformation of space-time and so on. And eventually it led him to the theory of relativity.
Mm-hmm.
So by thinking of these thought experiments, right? So he was just thinking, I fall and I have this red ball nearby, and boom, gravity came about. So thought experiments is one key thing. The other, like I said before, is computers. Often we say, I have this crazy stuff, and everything goes on, and I put it in a computer. And I ask, okay, I cannot compute all these things. I'll ask the computer to compute. And the computer will crunch numbers, and a few days later tells me, okay, the result is 7.3. And then I have to go and develop totally different tools that could run some computation in pen and paper and give me this 7.3.
Mm-hmm.
And now I have some hints from computers. So computers are like a way of creating your own universe. Are like thought experiments, but with numbers. So you just say, I run my computer computation, and I have this prediction for what it could be. And recently in physics, there are other ideas that are now emerging as alternatives for studying these theories at a very strong coupling. And we might at some point discuss some of these ideas that go by the name of holography and ADS-CFT, and that are new descriptions of physics that sometimes give you a totally different perspective on a problem. You are stuck on trying to understand this problem, and then a new idea comes that says, well, actually, this problem is equivalent to this other problem that's totally different. Mm-hmm. And now suddenly you are attacking a problem and you have two different descriptions of the same thing. You have two different approaches that you can use. And so that's another concept in physics that often appears that we use, which is this concept of dualities or correspondences, which are often in physics there is more than one way of describing the same thing, right? Like a fluid in a swimming pool, like we said before. One way of describing is just describe where is the water, how is it moving, and at what velocity, what's the temperature, is it too cold, is there too much salt in it, and you describe the properties of the water and the fluid that's moving in the swimming pool. Another description would be you zoom in and you see, it's just a bunch of atoms, and you describe the position of all the atoms and where they are and what they are trying to do, etc. And of course, it's the same thing.
But that sounds much harder.
But the atom one sounds much harder in this particular case. It's true. In fact, what happens is that the atom one is much harder because there are many, many more atoms and so on. But it's also more fundamental because it's the same atoms that describe the movement in the swimming pool that will describe water vapor. That is totally different, right? So if you have water vapor, it's the same molecules of water that describe water in the swimming pool and that describe a tsunami, right? And so tsunami, the swimming pool, and water vapor, it's more or less the same thing. Ice is also the same thing, right? So it's the same molecules of water. And so what happens is that sometimes the rules at the microscopic level, the rules for these atoms that will be the atoms of water are very, very simple at the microscopic level. But then, because you put so many of them, and even with a very simple rule, complicated emergent phenomena appear. And you can get ice, you can get vapor, you can get liquids, you can get all these different things out of very simple rules. It's like in a game. You can have a game with very simple rules like chess, and then you have these beautiful games that people say, oh, wow, this was a masterpiece, how amazing, and so on. And the rules of chess are the same, but then some games are amazing, and some games are boring. And similarly with water. Some phases of water are very boring, and the most exciting phases of water are in the transition between liquid and vapor, and when it's really transitioning. And then it's where these quantum effects become more important and where everything matters, and that's where, even though the fundamental rules are the same, the emergent phenomena, the emergent effects can be much richer and than the fundamental rules. Now, it's true that the fundamental rules can be simple, but indeed predicting what's happening at an emergent level, it's often very complicated. So in that sense, it's easier to use the equations that describe the water in the swimming pool, of course, than describing all the atoms in the swimming pool.
You said that the hard problems that you're working on in quantum field theory require new tools. Can you tell us what some of these tools are that you use to tackle these very difficult problems?
Like we said in quantum mechanics, what happens is that many things happen at once. And you cannot really say for sure what's going to happen because everything is happening at once. And so when I told you that particles travel from a flashlight from a point to another, they actually do many things at once. And in particular, even to say that particle goes from A to B, you cannot know for sure that it goes from A to B. You can only compute probabilities. And so physics is all about computing probabilities. There is some probability that it goes from A to B, but it can go from A to C, it can go from A to D, it can go from A to any other point. And so at the end of the day, what you are studying are what are the probabilities of something to happen in physics. And sometimes to do these computations in physics and to compute all this, what's the probability for something to happen, you have to do these long computations, and you have to develop these new tools. But you could flip it around and say, well, if it's a probability, it's a number between 0 and 1, right? And then you can start saying, and you can ask, instead of doing the computation, let me think what could be the possible results of this computation. It's a probability, so it's a number between 0 and 1. It must respect the rules of causality and relativity. So if I'm very far away, I cannot influence what's happening here right away. And you start thinking, instead of doing the computation, is there a way of trying to constrain, to fix, we call it to bootstrap, what could happen just by trying to impose very fundamental principles on the result directly? So instead of trying to describe what is really going on, can we think of a question, a physics question, like what's the probability of a photon reaching my hand, coming from Lorentz hand? And then instead of trying to do this honest computation, let's try to fix the result, to ask what are the possible outcomes of this result. In any possible theory, we might not even know the rules of the game. We might not even know the fundamental theory that we could be studying quantum gravity, say. And this is a new perspective. It's called the bootstrap. And it's the idea of trying to use very fundamental physics principles, quantum mechanics, relativity, some very simple mathematical principles as well, we call them analyticity, and trying to use these fundamental physics principles that we believe are sacred to try to carve out the space of what is possible and what's impossible in a given experiment, in a given physical quantity. So this is a very different way of thinking. Instead of thinking I have one theory and one computation I have to do, and I don't know how to do the computation, and I try and I try and I try, I say, no, let me take a step back and say, there is some theory, there is some computation, I don't know what the computation is, but I know that the result must be compatible with the fundamental principles of physics. So what could the result be? And so this is a new approach. Now, typically what you'd study in this approach is then you ask these very general questions of what could be the outcome of some experiment, what could be the outcomes of some probability of some experiment. And of course, just by thinking of what could be possible and what is impossible, you cannot get the 7.3 that I mentioned before. You cannot get a sharp number. But you can say, well, it could be between 5 and 8, say. And then you start inputting more physical principles. You start saying, oh, and I also want to impose a little bit of Einstein theory of relativity and so on. And now you run the thought experiment of what could happen, and you get between 5.3 and 7.8. And you start squeezing the result. You start squeezing the possible outcomes of what's possible and impossible. And the question we might ask is the space of what's possible and impossible? That's not a one-dimensional space, because there's not one experiment. There are millions of experiments we could do, so it's an infinite dimensional space. So you should think of it as like a sculpture in infinite dimensions. And the inside of the sculpture is what's possible, and the outside of the sculpture is what's impossible. And how is this space? Can we study this metaphysics space, this space of all possible physics outcomes? Can we study it? Does it have nice features, like a nice sculpture? Does it have pointy edges, pointy corners? So that's something we are trying to understand, that many people are trying to understand, is what is this possible space of theories? And can it be that some of the theories that we struggle to solve because they are so strongly coupled and the quantum effects are so strong, could it be that they occupy special places in this space of theories? Could it be that there is special points in this landscape of what's possible and impossible, and perhaps there are special points, some tips of some corners of this space of theories, and perhaps there are some locations that are privileged and that could indicate for exciting things going on. So that's one approach.
You said this is the bootstrap approach?
This is the bootstrap approach.
That seems like such a real world nitty dirty bootstrap. Can you explain what it means in this context?
Right. So the bootstrap alludes to an impossible picture. It's the picture that you hold yourself from your bootstraps and you push, and then you are flying. You lift yourself out of the air by pulling off your bootstraps. And why is it related to what I said before? Because I'm trying to get the result of a computation without doing the computation. That really looks impossible. I should not be able to get away with that, right?
That's like yanking yourself into the air by
it's
your
like
bootstraps.
I want to know this result, 5.3 to 7.8, without doing the computation. How come? Why? How could I do it? And that looks counterintuitive. It looks strange. And that's why we like this picture. Now, it turns out that why would this be possible? And it's possible because physics is such a beautiful, but at the same time, rigid framework, right? So it's amazing that things can work, because so many things need to work at the same time, right? So you need, with the same rules of electromagnetism, to explain radio waves and properties of matter and electronics and spectrum of the sun. The same rules need to describe so many things. And so everything is so rigid that if you ask, could I change this parameter a little bit? Here, I want to explain some physics experiment where in some material I got some blue line instead of some red line. So I'll change this law of physics. But then everything else will fail, right? So you cannot just change things at random. So everything is very, very rigid. So even without doing computation, sometimes because things are so constrained. Just by thinking what could happen, you can indeed nail things down.
Something
And,
within the realm of possibility versus
within
not.
the realm of possibilities
Right.
versus impossibilities. And so, and it brings us back to this power of thought experiments, that this is often built on thinking, suppose I want to study this probability. It needs to be a number between 0 and 1, but if this number was 0.7, it might imply that the outcome of another experiment, another thought experiment, would be 1.3. But probabilities cannot be 1.3. They need to be smaller than 1. And then that 0.7 needs to be excluded. Okay, so let me try 0.1. But 0.1 would then imply that this other experiment would predict a signal arriving there faster than light. Okay, so then 0.1 is also excluded.
Right.
And by just thinking about all these thought experiments, now we are starting to squeeze the space of what's possible and impossible, and we are getting to a smaller and smaller space.
It's like detective work.
It's like
eliminating the
detective work.
possibilities.
Yeah, it's very much like detective work.
I think this type of approach is usually referred to as a bottom-up approach, whereas some of the other ones are called a top-down approach. In general, what are the types of situations where you want to use some kind of bottom-up approach versus a top-down approach?
Exactly. Yeah. So there are indeed these two descriptions. I confess that I always mix them up, so I will not try to use bottom up and top down because I never know which one is which. But I know such thing exists. But basically,
Your boots are on the bottom, so you. Anyway, I don't know.
I never know which one is top up, top down, bottom up. Yeah, for me, I never understood the logic between that. But indeed, there is this picture that you can try to understand the rules of the game, the rules of the world, by either trying to get the very big picture, what could be the possible and impossible, what can happen in the most general situations. And the other way you could make progress is saying, no, let me pick one special example and learn that special example in great, great detail. And so those are two very extreme ways of getting knowledge, right? Totally big picture. I mean, it would be like saying, what do we have in common? We all want things. We all move from one place to another. We all have anxieties, etc. That's a very general way of describing humanity, right? Or you can just follow one person and learn about all its inner desires and so on. And even though it is just one person, if you really learn about everything that person feels or thinks, you really learn a great deal about humanity. And so in physics, it's the same thing. You can either get the full picture of what's happening in all possible generality, but then you will not go as deep in any particular direction. Or you can say, let me focus on one example and let me go really down along that rabbit hole and try to understand everything from all possible points of view about that particular problem or that particular theory. And in that way, based on that particular example, try to then draw general lessons that could be valid in much more general situations.
You said we can think of what it gives us as, an ice sculpture or some complicated landscape with these peninsulas or islands or different things. So is the ultimate goal to try to figure out where our reality, our world fits in, and this is just some point in one of these landscapes?
Right. Exactly. So we could imagine we have this map, and there's this cross, you are here. And now there are two possibilities. Maybe we carve out this map of what's possible and what's impossible, right? And maybe this map is like Canada, and maybe we are at some point in the middle of Canada. Well, then it's hard to find us, right? If you are, Canada is very big. If you are in some random point in the middle of Canada, no one will ever find you. But if you are at the tip of the peninsula or in the middle of a very small island or something, those are special points you could look at. And it so happens, and sometimes we understand why, sometimes we don't understand why, that often the most interesting theories are lying in these most interesting spots, these corners, these tips, these places where you cannot go any further. It's like at the boundary between what's possible and what's impossible. Now, why would people live at the boundary? well, that's where people live in Canada, right? They live at the boundary between the US and Canada, right? Why? Because they were trying to go down because it was warmer, and then they stopped where they could not go anymore. So with physics, it could be the same thing. The theory could try to go in some direction because it wants to maximize some physical principle, and he wants to increase the entropy or something, and it's trying to move, and then poof, cannot move anymore. So I got stuck here. And then it's the boundary between what's possible and impossible. And so if there's some underlying principle that we might not know that is trying to push theories in some particular direction, then it's natural that they stop where they cannot go any further. And that is the boundary between what's possible and impossible. Mm-hmm. And so that gives us hope that if we could carve out this space of what's possible and impossible, it's probably at the boundary that the most interesting theories are, if indeed such principles of wanting to go towards something, like again in countries, we want to go towards the water or towards the warmer climate typically, right? And so there are these two principles that push you towards water or warmer climate. If there is something similar in physics that pushes you towards, some information theoretical principle or some entropic principle or something that pushes you in some particular direction, then you would expect interesting theories to lie at the boundary. Mm-hmm. So far, that seems to be what we are finding when we study the space of the interesting theories, and then we try to put these crosses of we are here, or interesting theories here, another interesting theories there. These interesting theories and these crosses of where we are seem to indeed be very close to the boundary as far as we can tell.
Mm-hmm. One thing I really love about these explanations that you give is you're helping to have us develop these really nice pictures in our head. Just now you're telling us about these landscapes and peninsulas and making connections to the Canadian border. And earlier you were telling us about quantum field theory. You were talking about membranes and bubbles, these kinds of things. It can, rather than just having to resort to math, we can develop these nice pictures. I also looked at some of the titles of your papers, and you had some other nice expressions which I don't understand, but I can picture them, like spinning hexagons. There was a paper about stampedes, non-zero bridges. So I'm just curious about these kinds of pictures that you help us to create when you're making these explanations. Is this fundamental to helping you to understand these concepts, or is this something that you do to help communicate the work to the public at the end?
No, I think it's both. I think the style of physics that I do, I like to have a graphical picture of what's going on, to have some kind of picture of what's going on.
In your head, or are you actually sketching out pictures as well?
Both. Mm-hmm. Both. This stampedes example, for example, is really literally processes where particles are moving in a tight space. And therefore, it's really like a stampede. They are moving and hitting each other and trying to pass from one point to the other. And you could ask, could those type of stampede-like behavior happen at the most fundamental level of nature? Could gluons sometimes try to move from one point to the other and be hitting another gluon and say, get away, let me pass, and pushing each other and trying to move from point to another, like a stampede? And indeed, we found some limits where in some physics situations where particles are trying to move at the speed of light from one point to another, and because they are forced to move at the speed of light, if a bunch of particles are trying to move at the same time at the speed of light, they will be on top of each other. Mm-hmm. There's only one speed of light. And then they will make these stampedes and they will try to interact with each other. And that was cute because then we looked at there are some techniques for studying these stampedes. Actually, people that study these stampedes, they study them in very different situations, like boarding an airplane. Like who boards first, and maybe not in Canada. In Canada, probably people board in a steady way. But if you're trying to board an airplane and you hit each other and so on, or in traffic jams and so on, when the cars need to slow down and accelerate and so on. And so there are techniques developed for counting how many ways it's possible to board an airplane or to move in traffic. And those same type of counting ways will be the same kind of counting techniques that we use to count how many ways the gluons can move when they have to move at the speed of light to go from point A to point B.
This is kind of going back to earlier when you were telling us about some of the tools that you make use of in studying these quantum field theories. And I know another one that you, I think, said, but we didn't talk about too much, is holography, which is making some of these connections, but in different dimensions. And could you tell us a little bit more about this tool of holography?
Yes. So before mentioning holography, let me mention again a little bit about this emergence. So this emergence is the idea that something that emerges that was not there, that again, like a beautiful chess game, the chess game by itself is not beautiful, just the horse moves like an L and the pawn moves by one step, and then suddenly beauty comes out of it, right? When the game is amazing. So beauty was not there, and then it comes about. It's the same thing with a fluid, like we said. A fluid is just made of atoms. So this notion of something being fluid and smooth and so on, it's an illusion. It's something emergent. It emerges because we are not looking very, very closely. So we could say that a fluid emerges when we zoom out. When we look from far away, then yes, a fluid exists. A fluid makes sense. But when we go in, oh, it was fake. Right? Same with temperature. Right? What is temperature? Temperature is nothing. There's no such thing as a temperature. What exists are particles moving around. If particles move very, very, very fast, you put your hand there, and the particles moving very fast will hit the particles in your hand, and now the particles in your hand are moving very fast, and your hand is warmer. And that's what touching a hot thing means. You touch a very cold thing, the particles in the cold object are not moving, so the ones in your hand, they are moving, so you touch them, and now the ones in your hand, they shake the ones in the cold stuff, and therefore they lose energy because they have to waste energy to wake the other ones up. And therefore your hand cools down. So what exists are particles moving and particles dancing. But what emerges is this notion of temperature, is this idea that there is such thing as being hot, being cold. But again, that's emergent. What's fundamental is particle moving. Now, in physics, it's not a shock if I tell you, no, it's not really, temperature is not really something fundamental. What's fundamental is particles. No, fluid is not something fundamental. What's fundamental is particles. But a more recent idea that is pushing this idea of emergence to an extremum is saying that perhaps even gravity, even space-time is emergent. Perhaps even if you want reality, even us, we don't exist. We are emergent, right? And the idea is that we, say in this room, we are here in 3 dimensions, right? We might be the image of an hologram, like Princess Leia, right, in Star Wars, right? So we might be a bunch of holograms here, and maybe we don't exist. We are just projected holograms into this 3-dimensional space, but we are actually just being generated by a 2D hologram at the boundary of the universe, say. Now, this seems like a crazy idea, right? If I say we don't exist, gravity doesn't exist, space-time doesn't exist, it's all emergent, it's all an illusion, and we are all an hologram. So let me tell you a little bit, where would such strange idea come about? That there could be something like a membrane, an hologram that could describe something inside. Now, the idea comes from the following, by thinking about information. So there is this fundamental idea in physics, which is that mass always grows. There's always more mass. In physics, we call it entropy, right? So entropy is always increasing, right? You break a glass, the glass, you get pieces all over, right? And the glass is not going to reconstruct itself into a beautiful glass, right? So things always increase. The entropy is always increasing. So we dying is because our entropy is growing, growing. Eventually we die. When we clean up our room, something that's very popular these days, you have to clean up your room. When you clean up your room,
you're a father, aren't you?
When you clean up your room, you are reducing the entropy in the room, right? But the entropy, I said, always needs to increase. So what's happening is that to clean up the room and to reduce the entropy of the room, you are increasing your own inside entropy, and you are coming closer to being dead. So, So
I've never thought of it that way.
yeah, so be careful when you need to clean up your room. So entropy always grows, and so there is this notion of disorder. Things always grows, and entropy also quantifies the amount of information. If you have an empty room, it cannot be messy. If you have a room full of books, it can be very messy, right? You can tear all the books apart, throw pages around, and so on. So the more mess you have, the more potential information you have. Mm-hmm. Okay, good. Now, let's try to make a really, really, really messy room by throwing more and more stuff inside the room, right? So we have this room, and we keep throwing books, like we said. We throw some ketchup. We throw lots of stuff inside the room to make it really, really messy. So what happens? Well, what happens is that at some point, the room is so heavy, so full, so big, so full of stuff, it forms a black hole.
So this is a thought experiment. You haven't made a room this messy before.
Well, you should see. But no, not that messy.
Not with ketchup.
No, the ketchup was missing. And so you have this idea that things can be messier and messier and messier and messier, and eventually they form a black hole. But if the mass is always increasing, and if eventually you form a black hole, it means the black hole is the messier object there is, right? Because it's the end point of a messy room. Mm-hmm. And so that means that the amount of mass, the amount of information is biggest in a ball if that ball is a black hole, right? Because as we said, we put more and more stuff, more and more information is there inside, and suddenly we have a black hole. On the other hand, a black hole, because it's such a simple, after all, object, much simpler than a messy room, it's just a black ball where light gets in and cannot get out, there are things we can compute, we can study about black holes. And we can quantify how much disorder, how much of this mess there is. And when we compute, when people computed, people like Bekenstein and Stephen Hawking and many people studied, asked, what is the amount of disorder inside the black hole? They found a very surprising thing. The bigger the black hole, the bigger the disorder. That's normal, right? If a room is twice as big, the disorder can be twice as big inside. But it was not proportional to the volume of the black hole. It was proportional to the area of the black hole. And that's very surprising, right? If you see a huge building, and you see a building that the volume is twice as big, you say inside there can be twice as much mass. Mm-hmm. You don't say the mass is proportional to the area of the building. When would you say that the mass is proportional to the area of the building? If all the mass is in the wall. That's the only scenario where you would say if a room doubles in area, the mass doubles. Mm-hmm. If someone tells you that, then you say, oh, inside that room, you just have a bunch of papers on the wall, right? Like the serial killer investigators, right? With all these strings and newspaper clips and so on. Everything is on the walls. There's nothing in the middle, right? Because then the wall surface doubles and the mass doubles. And so what we are saying is that we were throwing information in this room. We form a black hole. And now we can describe this black hole, and the amount of information is only at the boundary. Mm-hmm. It's only at the walls. It's only at the end. Well, but then if you take this seriously, it means that you should be able, if even in the most extreme situation, where you have the most amount of information, if it's possible to describe it just by looking at the wall, when you have less, you should also be able to. And so the ultimate conclusion of this crazy thought experiment is that you should be able to describe what's inside the universe by describing the boundary of the universe. Mm-hmm. Okay, now this could be a dinner chat, right? We are having some drinks and we are having some fun, and we come up with these crazy ideas. But then, in 1997, Maldacena said this is not just a crazy idea. Here is one theory of quantum gravity that describes an example of what could be a universe. And here is an hologram at the boundary of this universe, and they should be the same thing. Mm-hmm. And this idea, that you could not only speculatively, but really write equations that says this reality is equal to this description in terms of an hologram that is just at the boundary of the universe, is what's called holography. It also goes by the name of ADS, CFT, or gauge gravity dualities. These are all names for the same thing. And it's a concrete realization of what was before a crazy idea that came mostly from these thought experiments with the black holes, right? Because if the idea is that everything can be described by the walls, but we don't feel like we are stuck to the wall, right? We feel like we are here. Mm-hmm. So what's the way out? Everything is described by the wall, but we feel like we are here. Well, then maybe we are an hologram projected from the wall, right? And maybe all the information is on the wall. And if you really look at the wall, you see all the rules of the game, the analog of the atoms in the water. Mm-hmm. And you see in the wall, the electrons and the chips and the quantum computer that is at the boundary of the universe. But then from far away, you have these Princess Leias, which are us, and this hologram is being projected in, and we emerge. Mm-hmm. And even the inside of the wall, the universe, the space, the gravity would emerge. We would all be emergent concepts mm-hmm. that would be produced by this quantum hologram. This idea would have far-reaching implications because it would tell you that gravity, for example, would be emergent. And at some point, we said, it's very hard to put gravity and quantum mechanics together. And what this idea would say, yeah, throw away gravity. Gravity doesn't exist. Gravity is emergent. Mm-hmm. All that exists is quantum mechanics in this quantum computer that's the hologram. And then gravity is fake news. It's just, you think there's gravity, but it's like you have an hologram of a colibri flying here, and it's not flying. It's just an hologram. And that could be how the world works. Maybe the world is holographic. Mm-hmm.
Well, Pedro, we'd like to share with you now a question that was sent in by a student. She'd like to ask you to say a little bit more about ADS-CFT.
Hi, my name is Anna. I'm currently a Sci student at Perimeter Institute, and I have the following question. Could you give the main gist of the so-called ADS-CFT correspondence and explain why people in your research community are so interested in it, even though we probably live in a different type of universe, not anti-de Sitter, but de Sitter space?
Let me go one step back and say, we had this thought experiment of the messy room that led us to this idea that there should be some hologram description of reality. Okay, someone tells you that, it's like one of those emails. I have a theory of everything, but okay, fine.
We do get a lot of those emails.
We do get a lot of those, okay. What can I do? You have to be a bit more specific. And then, and it's hard. And I don't know, and no one knows, what's the hologram that describes our universe. Then we ask, is there a toy universe, a toy theory that we can play with, which would be an alternative universe, a simpler one, where you would have, in that universe, you would still have gravity, you would still have particles, but it would be a toy theory. And in that toy theory, you can make these ideas precise. And at least you have a laboratory, a mental laboratory, where you can exercise and practice and test these ideas and see if they make sense and push them forward. And it's related to this bottom-up and top-down approach, and I never know which one, that Lauren was referring to, and that would be amazing. And indeed, we were able to make these ideas precise in some toy examples. And this question was referring to that the examples we describe, we managed to make this precise, are toys. They are not the real thing. And so given that they are toys, why do we like them so much, right? Like, okay, why don't we care about the real thing and not about the toy? And as usual, the answer is we start first trying to understand these toys, And now there are two possibilities. Some people will try to make these toys more and more realistic. Try to say, I will try to add more and more ingredients to make this more closer and closer to the real world. Some people will stay longer with the toys and say, no, I want to play with this toy a bit longer. I want to go deeper and deeper and try to extract more lessons from this toy. And it's a spectrum.
Mm-hmm.
ADS is related to the name of this toy. It turns out that it's better to describe these holograms if there is a wall, right? We need a wall to hang the hologram, right? And if you have just a regular space-time, imagine space-time that goes on forever. Where's the wall? There's no end. You just go when you are waiting for a place to hang the hologram, but you don't find one.
Mm-hmm.
So it would be better if your space-time was a very big box. Because when your space-time is a very big box, you go to the boundary of the box and you put the hologram there. And ADS is a box. It's a space-time that's a box. There is a boundary. There is an end where you can put this hologram. Now, I should say it's a fantastic box. It's not a random box. Let me tell you something special about it. Let me give you an example. Take a shoebox, right? Mm-hmm. There is a midpoint. There is a point which is the middle, right? And then there are the corners and the walls and so on. But there is a special point which is the middle of the box. This anti-de-Sitter is a box, but there's no middle. All points are the same. There's no special point. Why do I call it a box? What is special about the box? Because I take this red ball here and I throw the red ball and I'm talking to you and I get hit by the red ball again. So I say this is a box. I throw the ball and the ball comes back. And I'm here and I throw this red ball and I get it back. I throw it and I get it back. I throw it and I get it back. It doesn't matter which direction I throw it and I get it back. Mm-hmm. It doesn't matter where I am in space-time. When I throw the red ball, I get it back. So in that sense, there's no center. Mm-hmm. It's all the same. Wherever you are, you take a red ball, you throw the red ball, you receive the red ball back. Right? So you feel like a box. But if I feel like a box, Colin feels like a box, everyone feels like being at the center of the box. Mm-hmm. It's a very democratic box. So it's the most perfect box there is. It's called ADS. It stands for anti-de-Sitter, which is the name of a geometer that thought about this box. And in this box, in this very big box, we understand that what happens inside the box can be described by an hologram at the boundary of this box. Now, we don't live in a box, right? We don't. At least we don't know if we live in a box. Maybe we do. Maybe the boundary is very, very far away. But one thing you could say is that whether we live in the box or not should not matter if the box is huge, right? Should the rules of physics here for us change if in a gazillion parsecs there is a wall? Probably not. It's really, really super far away. Who cares? Mm-hmm. From that point of view, some people, I would say, that if you can think of physics with a fake box, provided you say the box is big enough, and if with that fake box you can describe what's inside, you can always pretend the box is big enough that it doesn't matter that if we are inside the box or not. If you can learn something about physics inside the box from a big box, that's good enough. Mm-hmm. But I say this because I don't know how to do holography if I have no box. If I knew, I wouldn't say this. I would just do holography without the box. Mm-hmm. If I knew how to realize these crazy holographic ideas directly in our universe, which goes on forever, I would prefer that. And so some people are trying. Even some people here at Perimeter, like Sabrina and others, are trying to study better what happens at infinity in the universe. And is it really impossible to put an hologram there? Do we really need a box? It would be good if we could. Mm-hmm. So there are things to understand. And things get even more subtle when you think about cosmology, when you think that the universe is expanding and it's growing. And then it's even harder to imagine where do you put the hologram in. Mm-hmm. Like the walls are growing and it's hard to put the hologram somewhere.
And we have one more question that was sent in from another colleague of ours here at Perimeter.
I'm Gang from Perimeter Institute. My question is that I have heard that you said you have solved a quantum field theory a few times. I wonder what that exactly means, and when will we actually solve quantum field theory?
So why do we say solving? Solving means computing. It means so if I want to study a physical quantity, we have to take our theory and understand what are the rules of the theory, what's the outcome of the experiment, and how do I go from the rules to the outcome of the experiment. Sometimes we can bypass that step by doing these bootstrap kind of ideas and studying what's possible and impossible. But then we have toy theories and real theories, right? And so again, it's like describing, say, the trajectory of a tennis ball, right? If I just say it's a parabola, there's gravity and so on, it's easy. If I say no, but there's wind, now it's a bit harder. And then I say, oh, and the material of the ball is, pieces of the ball are falling as it's going, now it's harder. So the more realistic you make it, the harder it is, and you can never really do a perfect job. You do better and better and better, but there's always more effects to take into account. So when are we going to solve real-world quantum field theory and be able to wake up and with a clean page of paper and at the end of the page compute the mass of the proton? I don't know. That would be amazing if I could compute the mass of the proton even with 2 digits in my lifetime. I would be delighted. Mm-hmm. We know the answer to this, right? We can put it in computers or we can measure it. We can take a scale and figure it out. But computing it from first principles, we don't know. Now, on the other hand, solving quantum field theory means developing techniques, new techniques, that we can use to do better and better in quantum field theory. And that requires solving these toy theories and understanding how to develop these techniques in simplified examples. In the same way that if you want to solve chess, you will solve checkers first. It's easier, right? Mm-hmm. So you will develop computer techniques for counting all possible checkers or for developing artificial intelligence for solving checkers, and then you'll apply it to chess and then to Go and eventually to give dating advices and so on. So, so the more complicated it goes, you will develop step by step, right? And so similarly with physics, what we want to do is be able to tame these quantum effects, and in particular these strong quantum effects, in the analog of checkers, in the simplest possible case.
Right.
Let's have at least one example where we can do it. And if we can really nail one example down, everyone will believe, okay, now it's a question of time. We have to work harder, but we'll do the next, we'll do chess, and then we'll do Go, etc. But we need the first example. Mm-hmm. And it was the case in other areas of physics before, like statistical mechanics. We needed to solve one statistical mechanics system. And there was a beautiful solution in 49, I believe, of the so-called two-dimensionalizing model, which is a particular model in 2 dimensions of statistical mechanics of a particular 2-dimensional material. And it was the first example that was possible to solve exactly. And then it was like a Pandora box. Once that one is solved, many others followed afterwards. And we learned many general lessons about phase transitions and properties of matter and so on. The quantum mechanical solution of the spectrum of the hydrogen atom, right? The energy levels of the hydrogen atom that we learned in school. It was crucial to have that one solution exactly. Mm-hmm. And then we developed techniques, sometimes exact, sometimes approximate, for studying many other atoms. And now we know chemistry. Mm-hmm. Right? And so it's often about breaking this barrier of solving a quantum field theory. Solving a quantum field theory is like solving a game, and there are easier games and more complicated games. And And even solving a game can mean many things, like chess is solved when you have 7 pieces on the board. If you have more than 7, it's not completely solved yet. Okay, so chess with 7 pieces, done. Chess with 9 pieces, not done yet. Mm-hmm. And similarly, in quantum field theory, in some quantum field theories, we managed to understand, for example, the analog of the spectrum of the hydrogen atom. What are the energies of that quantum theory? What energies can the states have? So that was something that we did, and that was probably greatly why I am at Perimeter, was because we solved that problem. That was a tough problem. That was an open problem in the field. How do we compute those energy levels? But that's the first thing we ask about the hydrogen atom is what are the energy levels? Then we ask, okay, now I take 2 hydrogen atoms and I throw them against each other. What happens? Oh, that's much harder than just studying the energy level. And then once we do that, we ask the next question. And that's like solving chess step by step and in more and more complicated situations.
So it's like you start with a toy, you solve that toy model, you make a more complicated toy, you solve that, and maybe someday this toy can be so complicated that we can solve it and then represent the universe.
Yeah, that's the hope, yeah. It's also the hope that sometimes that physics tends to look more and more like a toy, in the sense that it's often the case that physics looks complicated, and then we find these unifying principles. This idea that there was, say, electricity and magnetism, and there were some laws for electricity, some laws for magnetism, and it was complicated, and then we understood, oh no, they can be combined. Mm-hmm. And actually things are simpler. Mm-hmm. And it's not like we have the electricity and the magnetism and so on. No, they really talk to each other, and there's a single thing. Mm-hmm. And now it became closer to the toy than to the real world. Mm-hmm. And so it's also the hope, but that might be just a dream, that the world can be closer to a toy, and that perhaps the fundamental rules will link things together that right now look very complicated and disparate, and there doesn't seem to be a connection between the expansion of the universe and the mass of the electron or whatever, right? So there are many things in physics that look totally independent and different from each other, that maybe once we will understand really what are the rules of the game, maybe they will be connected and maybe things will be simpler. So it might be that the goal is not create a toy and make it more and more complicated, but understand what are the underlying rules, and perhaps the fundamental rules will be the toyest of all toys, right?
When we started this conversation, Lauren admitted that she was a little intimidated because of all the terminology, quantum field theory, and I can emphasize that I was 10 times more, 100 times more, because I haven't studied physics in university. Lauren's a quantum scientist, and she was intimidated. But I want to say that just to reiterate that your ability to draw pictures verbally, and then I create them in my head. I don't know what your sculpture looks like of what's possible versus impossible. Mine is a very cool quartz crystalline structure. But the idea that you can convey these ideas in a clear way, I think it relates to your teaching as well. You've done a lot of teaching and outreach, and I think you two have worked together before on teaching. Can you talk about how you approach teaching these subjects to younger people? And you even do outreach to non-scientists like myself.
Yeah, so I like teaching very much. I think it's one of the most exciting things about what we do. I mean, especially the teaching that I do, which is a huge privilege, is that we get to teach, first of all, amazing students that are really super excited about being here, and no one is studying some particular physics subject because you have to get some grades or some credits. No, people are really excited and they want to learn physics because they really are passionate about understanding how nature works the way it works. And often to teach, you have to really understand things in a very deep way if you want to simplify it. It's easier often to protect yourself in the math. So writing equations is easy. Solving equations is easy.
Says you.
No.
But I'm a non-scientist. I see where you're coming from.
But it's something mechanical. It's something you learn. You have to learn how to do it.
Or you learn to ask a computer to do it.
You can ask the computer to do it.
You have to know how to ask the computer, or know what to ask the computer as well.
it's a language.
Mm-hmm.
It's a language. You learn it, right? So, but teaching forces you to have a clean picture of the fundamentals, to not to be lost in the technicalities and details that sometimes don't matter, but really focus on what is really the problem we want to solve, what's really simple, what's really hard. And I think that's very important for a physicist to keep some mental sanity, is to teach. Teaching too much is not good, then you don't have time to do research. But teaching a good deal, I think, is very, very powerful and useful. In particular, when you are teaching some of these subjects that are not yet in textbooks or that are a little bit more advanced, you are really often going into the unknown, going into the world of what is not yet known. And then as you try to understand things and try to bring them to the students, you are trying to cleaning it up, purifying it, and really polishing it. And it's really something precious that you are allowing yourself to tell someone. And when you explain the way you understood some high energy collision of two particles, and why when these two particles hit each other, things can fly in all possible directions with all equal probability, and you understood why was it all equal probability in that particular case, and you managed to simplify it. It's really a magical moment when you manage to get that across. So yeah, it's something transcendental that you go into this platonic world of ideas, you drag them down, and then you give them as a gift. So
Earlier in this conversation, you mentioned how some people in Canada, they amass along the border so they can be far south for the warm weather. But you spend about, half your year in Brazil at the South American Institute for Fundamental Research. Can you tell us how that came to be and what drew you there?
Yeah, that's true. So I spend a few months every year there. So I go back and forth. So it's convenient. It's the same time zone, more or less. So I go with a cloud of students, typically moving up and down in this strong coupled system. And so indeed, I first got to know this institute in South America. The goal of this institute, this cipher, that ICTP cipher that you mentioned, is to serve as a hub for all of South America for theoretical physics in South America. And so what happens in practice at this institute is that you have schools and workshops and conferences running all the time with students from all over South America going there for a week or two, interacting with excited students that are really passionate about a particular topic and, say, strongly correlated electrons, and then going back to their home institutions in Chile, Argentina, Bolivia, etc. And then a few months later, coming back to another event that happens there. And at some point, a community starts to emerge. Mm-hmm. You start to know people from the various places. People that were previously totally isolated, now they get to meet each other at Cypher. Top scientists from all over the world get to go to Cypher. And at the same time, you have access to this huge pool of 400 million people in South America, the best of the best that start to go there and that have an opportunity to be exposed to all these top people and then eventually come here and join us at Perimeter Masters International or come here for PhD or become future postdocs, etc. So it really serves as a hub, not only to connect everyone in South America, but to connect South America to the world more broadly. And it's a relatively recent institute. It's like 15 years. And at the level of what it does, which is organizing these schools and workshops, it's already one of the leading institutes in the world. I'm Portuguese, which the language is the same as in Brazil. The culture is similar. It's more or less the same type of culture, but everything is multiplied by 10 in Brazil. When people are happy, they are 10 times as happy as in Portugal. And people are sad, they are 10 times as more. depressed as if they were in Portugal. So everything in Portugal happens. Whatever I take that I know how it works in Portugal, I multiply by 10 and I get a good feel of what would happen in Brazil. So I have a good intuition about the culture. I thought this project, trying to create this institute and grow it, was exciting. At the time, I spoke with some people at PI that encouraged me to try to do it. We leveraged many of the things that we knew at PI to create things that are sometimes similar, sometimes different, because you have to adapt the different way of doing things. But for example, we translated all of the outreach material of PI to Portuguese and now to Spanish as well. People from outreach, Greg and friends, went over to Brazil several times to give workshops for high school teachers and students. And I gave several lectures on relativity and quantum mechanics on Saturday mornings for high school kids that wake up at 4 a.m. to take these trains to to go to attend these lectures and understand how space and time can morph into each other. And so it's lots of fun. I think the impact is huge and can be huge. I think it's obviously super useful for these students that otherwise would not have a contact with some researchers that are really doing research in these exciting topics. But it's also fantastic for us that we have access to this amazing pool of talent. When we'll finish this podcast, I'm going to chat with Alessandra that came from this program, and we are going to try to play a little bit more with these toy models that I told you about.
It's fantastic. We did have one more question that's less technical. It's from a young person here in Waterloo, so maybe we can play that one for you.
My name's Alice and I'm in grade 2. What would you consider to be a good day at your job?
Yeah. So that's a very good question. So what would I consider to be a good day?
The hardest question yet.
That's a very good one. So
Did we finally stump you? And it wasn't even a science question?
No. This is an excellent question. Yeah. So I think, as you said at some point, a lot of the work we do in practice is detective work. You are trying to think of many, many thought experiments and try to see, could it be that that this experiment result has anything to say about this other experiment result? And you keep trying, and 99% of the time you are trying out things, converting these thought experiments into equations, trying to solve equations, simplifying equations, not solving the equations you want, but solving simpler equations so that later you can solve the equations you want to solve. And then some days you crack one of them. Some days it works. You find, oh, this is the right question. So those are amazing days. And even better typically is when you do it in the blackboard with someone else. When sometimes you are in a blackboard and you are thinking, we need to, I don't know, understand the movement of these gluons when they are trying to move at the speed of light. And then someone points out, well, but if they are moving all together, they cannot pass by each other. Then someone says, oh, maybe that's about counting how things go when they cannot pass by each other. Could this be related to these counting problems of stampedes? And I think truth has this attractor force to it. It's like a basin, like water swirling around. So sometimes you feel lost. But when you are close to something that makes sense, close to something that is, oh, that's the right thing, it pushes you towards it. And so there are these moments where you are in the blackboard and you have this feeling that you are being pushed towards truth. And that's amazing. That's an amazing feel. You just go with the flow, and it's like a dance, and each of you are changing ideas, but you feel like, oh, we are going somewhere. And that feeling of following, letting you letting you flow, and you just let go, and you will eventually get to something awesome because you feel like you are moving closer to something deep. Is fantastic. So, but often you are just lost. You are scattered, you are moving left, right, and then suddenly there's this click and you feel like you found one of these streams that will swirl to something true.
Amazing.
It's a wonderful answer.
Well, this has been so much fun, Pedro. Thank you so much
thank
for
you.
sharing your time. I think we're going to be leaving with a lot of new lessons to ponder, and I think we're all going to remember not to let our rooms get too messy because we might create a black hole.
But if you clean them, you are closer to dying. So.
We'll just keep the room sort of tidy.
Yeah, that's good.